Hey. Okay. So today we will talk about offline reinforcement learning. So far we have been talking about reinforcement learning on a lot of several different settings. So let's first review on what we have been talking about. So the first setting, or most simplest setting, is like the planning setting, which we already know the transition and the reward. In that kind of scenario, there's not much learning in it. It's just planning, like I want to find a policy, optimal policy. And in terms of learning, there are three settings. The very first setting we talk about, the learning, is the generative model. Generative model, essentially, the interaction protocol is like we have access to this simulator, where for the simulator, we can basically query any state and action, and the simulator will output the next state and the reward. So we also has been talking about online setting, or online reinforcement learning, where essentially by online setting we mean we will this simulator allows you to just query any state action. Well, in the online setting, you have to start from the very beginning, like must start from the initial states. And we're doing learning through online interaction with MDP. Basically, we're an agent, and we can basically collect whatever the data we want, but we need to interact with MDP to collect the data. So we collect data by ourselves. And finally, we will talk about today is the offline setting. Well, in the online setting, we collect data by ourselves, so we need to do exploitation trade-off. In the offline setting, we actually learn from existing data. Collected by others. So such a kind of a scenario is like, for example, we want to do some ads, like advertisement, recommendation, like for Google. And in that kind of scenario, maybe it's like involves a lot of money. Google may not want to let you to test whatever the strategy directly online, because if you try some terrible strategy, Google will kind of lose billions of dollars a day. So in that kind of scenario, maybe a more safe, or the company's approach is more like you will collect the recommendation data by some other strategy, some existing strategy. They believe they can be performed reasonably well, and you hope you can learn from those existing data and to figure out what is the better policy, what is the optimal policy in that kind of scenario. So this is what we're going to talk about today in the offline setting. So how we formulate the offline setting? So typically is we say we have some behavior policy. So this is essentially what doing by others. Essentially someone has already used some behavior policy pi, or this pi can be non-Markovian, can be some other policy, and to collect a lot of trajectories. Hopefully this policy pi is also some collection, so it can be a lot of policy, that's also fine. And I think most important thing is we collect a bunch of trajectories, that is S1i, S2i, A1i, S2i, A2i, till SHI. And we have I from 1 to n. So in that case, each I corresponds to one trajectory, S1, A1, S2, A2, SH, AH. And we have n different trajectories. So this is what we mean by data collected by others. So this is like one of the settings we can consider offline reinforcement learning. And hope this policy is diverse enough. And if we have like see the trajectory for large amount of trajectory, so we can learn the transition and can learn the reward from this data. And for simplicity for today, we always assume reward is known. So we only need to learn the transition here. And sometimes we will also consider even more challenging setting where the data is given by the tuples. In sense of transition tuples. For example, we don't see the entire trajectories. All we see is like collected pieces of the trajectories. That is like, for example, I see a lot of collection of the tuples that is in the form of SHI, AHI, and SH plus 1I. I from 1 to n. So for each step, I kind of see a lot of this is transition tuples. And those are like independent. And this SI plus 1 is kind of like sampled from the transition distribution of SA. And we have like those kind of tuples for each step. So we want to learn the transition and eventually figure out the optimal policy from those data. So this is like the full trajectory. This is like, I don't even have the full trajectory. I only have just the tuples at each steps. And I want to learn the optimal policy from this. And it's clear like the second setting is definitely slightly harder than the first setting if we allow some augmentation of H sample capacity. Because if we have given the trajectory data, we can just generate the second version like by truncating it. Like by looking at this tuple as a first step and this tuple as second step. Okay? We can do some data splitting to get the second version. So this one is like harder. Okay. So intuitively, if we can do some offline reinforcement learning, that is, you want to learn the optimal policy from those like either trajectory data or like this transition tuples, we need to essentially say this data need to be somehow diverse. It should not like just specifically focus on one specific state and action. The data only has like one state and action. Then we only able to learn transition for that specific state and action. For other state action, I have no idea what it is. So we somehow need to have a notion of like this data is representative so that it kind of cover a lot of different scenarios and we can learn from it. In order to do that, we can, let's do some definition. Okay. So let this mu h SA essentially be the probability of visiting state action pair SA at a step H. So in here, like for example, let's look at the tuple scenario. We can basically say this mu h SA is roughly equal to the number of counts, how many times I observe SA at each step. Basically happens in this data. Like how many tuples actually start with SA and divided by n, the total number of tuples in this data set. Okay. This is like a number of SA, X, X means like it can be any next state in DH. So this can be like a true probability, and this is like more or less an empirical version. Empirical version is roughly this. And this differs by some like small concentration. In this class, for simplicity, let's just say this is equal. Okay, let's just pretend this is equal. So for simplicity for later derivation. But I think general, let's say this is like probability of visiting state action pair SA. So we say intuitively, we want this data to be representative so that it covers most like important assays. So basically, we should not just cover some particular, like one assay pair. It should like basically span over a lot of different assay pair, as long as those assay pair can be visited by some policy. So typically, one very naive assumption we can think of is this called all policy concentrability. Okay. So assumption one is called all policy concentrability. So the name is a little bit counterintuitive. I kind of always feel this is like a bad name. I don't know why it's called like concentrability. It's basically for some historical reason. But the more or less this assumption is about some coverage over mu, like how spread out like this mu is. So we say the all policy concentrability assumption basically says data distribution mu needs to satisfy the following assumption. Satisfies that max over H in H, SA in SA. So basically max over all steps and all state action pair. And then max over policy pi. We have the probability of, if we follow the policy pi, to visit state action pair SA at step H, divided by this data distribution mu HSA, is upper bounded by C. This is the probability of visiting this SAH, that is means visiting this state action pair SA at step H if follows policy pi. Okay. So this is called all policy concentrability because it basically says whatever the policy, like I need to max over all the policy. And so whatever the policy, I'm guaranteed this ratio is upper bounded. Okay. So that is if I have some policy that will visit some like state action for like big probability, then I need to have like a reasonable amount of data in my data set to like essentially support that. So the mu will not be too small. So this essentially says when p is not, this p pi, there exists some pi, p pi is not small, then this mu h should not be small. And although we wrote some C here, but remember this is like some problem-dependent parameter, so you should not consider this C as some constant. In fact, it's, usually it's not a constant. So let's consider like in a simulator setting. like simulator is like easier setting than offline. So in that kind of scenario, we can essentially collect data uniformly by like querying assay uniformly. Like suppose this is like how we collect the data. Let's just suppose this is like how we collect offline data. In that kind of scenario, it's not very hard to show that this mu-h, essentially the probability of visiting some SA at each step in this data set is just because we're querying them uniformly. So this is just 1 over SA. So we know the concentrability coefficient, this C. This implies C is less than SA. So we're already in C, like here, the C is not a constant. C is actually something scaling with number of states and number of action. So only in some like very special MDP you can see C as a constant. Otherwise, like C is usually something not as small. So this is definitely a very strong assumption, but basically this is like the first assumption we can think of. So that's why like we can consider this assumption first. So I think this is also usually how we approach the problem. We kind of like first come up with the simplest or strongest assumption, and we can see like then we will see like what we can see in that kind of what we can say in that kind of scenario. So after we get some reasonably like strong assumption, and the next question is what is the algorithm we're gonna do this offline reinforcement learning? So one of the very naive algorithm is just doing value iteration with this empirical transition. So we also just consider the naive algorithm first. So we will do value iteration. Using empirical transition. And recall that value iteration is essentially just doing Bellman equation, like doing the Bellman update and using dynamic programming fashion from the last step to the first step. And in that kind of scenario, in the Bellman equation, we need to know reward and the transition. And we here, for simplicity, we just assume reward is already known. So what we don't know is just transition. So for here, we just use the empirical transition to replace the transition in the Bellman update equation, where empirical transition is, we kind of have seen this for a lot of time, is just by counting the frequency, we visited some next state S prime within the data set. Okay. So it's like the ratio between the number of times we see this SAS prime tuple over the number of times we see the SA tuple in the data set. Okay. So the first question we may wonder in this offline scenario is, okay, I give the very strong assumption, and I have some naive algorithm. Is this algorithm guaranteed to find some optimal policy? Like, is this gonna work? Turns out, yes. So we will prove the theorem for this. Suppose data distribution mu satisfies assumption 1. Then, with probability, at least 1 minus delta, the value iteration algorithm we talk about here, this is the value iteration, outputs a policy pi hat that is epsilon optimal with if we have enough like number of data per step, that is with n equal to O tilde h fourth s c over epsilon square tuples per step. Okay. Just recall by epsilon optimal is like the standard definition where we say the difference in terms of value compared to the optimal policy is less than epsilon. Okay. So any questions about the theorem so far? So this is essentially just saying under the very strong assumption that is all policy concentrability, and also using the vanilla algorithm that is value iteration, we will be able to find the epsilon optimal policy as long as we have a reasonable number of data, where the data is like given this complexity that is h to the fourth s and this concentrability coefficient c over epsilon square. Q.
Is this n equals to O tilde? Is this condition such that that thing is equal?
What?
Is this condition like n equals O tilde h fourth s
Mhm.
squared? Is it that such that that thing is equal for that to concentrate that you?
Roughly equal, you can also say that, yeah. I think this number is like roughly the number required to make sure this transition, this estimation is like a well approximate the true transition. So we actually see that in the proof. So if you notice, this is like this sometimes is very similar to what we have in the like a simulator setting, but only difference is there is like h fourth SA or something over epsilon square, h fifths or something. But here we don't have A dependence, but we have C. But we note like this is not saying like this sometimes is actually better because usually C is much larger than A. So this complexity is typically like worse than the simulator complexity. Like for example, in this example, this C is actually SA. So this is like S squared is even worse than the standard thing. But you can essentially prove this is like relatively sharp for this like naive algorithm. So let's talk about how we're gonna prove the such theorem or like why this is true. So the overall proof structure is relatively similar to what we have in a simulator setting, where in a simulator setting we kind of like we do the uniform, we kind of like record the state action uniformly. Like we say this is like a specific mu h. Well, here you can essentially think our proof need to generalize from this specific mu h to more general any mu h that satisfy this concentrability assumption. So let's just briefly recall how we proved the simulator setting. It has been a few weeks. So I will just quickly recall that by doing in the simulator setting, I think the most important thing is we need to prove two lemmas, and essentially the final results is just a combination of the two lemmas. So the first lemma essentially decomposes the value difference to the transition difference. Okay. those lemma has been proved in the previous lecture, so I will no longer talk about the proof again, but you can look at the previous lecture notes to see how it works. We say for any policy pi and any state and step combination SH, we have the following. I think in that lecture, we kind of see the value difference, VH pi S, subtract by V hat pi S. Remember, this is like some imaginary value on the created MDP, which using transition like empirical like this p hat as a transition, and R. Okay, so this MDP does not exist, but we can pretend there exists an MDP where the transition probability is actually using p hat. So we write the value in this way, and we say this two difference is equal to expectation taken over m hat, where we say this is m hat. Okay, this is the fake MDP. If the trajectory is follow the m hat pi, and we look at the difference between transition given SH equal to S. So this is what we have been proved. We have already proved in the simulator lecture. If you still remember that, kind of decompose the values, difference in values for the same policy pi, to the difference in the transition. And essentially, transition we can use some concentration inequality to prove these are close. And by symmetry, we can also prove a similar thing. So we note this, the left-hand side is symmetric, that we have a V and V hat. Where on the right-hand side is a little bit non-symmetric because we have M hat here. Well, this is V, this is not V hat. And this is M hat, this is not M. So by symmetry, we can actually get another expression, which is by taking expectation of M pi. Okay, this is taking expectation over the true MDP, follow the policy pi. And we have summation I from H to capital H. Pi minus pi hat, Vi plus 1 hat pi SI given SH equal to S. So, yeah. So essentially, by symmetry, what we do is we kind of replace this M hat with M, but in turn, we need to replace this V with V hat. And you can check this equation also holds. Okay. So both version works. And particularly in this proof, we will use the second version. I think the second version is better. Is better for second version to use the concentrability assumption. Like this assumption essentially says you follow the policy pi, or the probability of follow the policy pi to visit SA. So this implicitly says you need to run on the real MDP. So this is like the probability generated by follow policy pi running real MDP. So yeah. So in order to do this, this is like more suitable. And if you use the first version, then it's unclear what is the probability. And the second lemma we use in a simulator setting is the concentration inequality. Okay, I will just write the version after the uniform concentration. So for any fixed value functions, where this values is in 0 to h to the power of s. So in this case, we kind of view value as some like a s-dimensional vector. And I think if you still remember, we say this is either fixed or basically can be random. But VH plus 1 is independent of PH hat. So as long as it's either fixed or is there some like independence in it, it's fine. So let's say if we have such a set of value function, then with probability greater or equal to 1 minus p for any SAH tuple in this SAH, we have the following concentration. That is pH minus pH hat operates on VH plus 1 SA. This thing is upper bounded by some absolute constant. Let's call it C0, so that is make it different from the capital C, which is a concentrability coefficient. This is like some absolute constant. Times H times iota over NHSA. Where this iota is some log factor. So second lemma, I think you actually did it in the homework. So I think you kind of like remember what it is. So those two lemmas are actually has already been proved in a simulation setting when we talk about generative model. So now we talk about how we're gonna use those two lemmas to help like getting the new guarantees for this offline scenario. So we'll do the proof of theorem 1. So the first step is very similar to how we did it in the simulator setting, that we decompose the value difference to 3 terms. The first term is V1 pi star S1. And then subtract V1 hat pi star S1. And then we add this term back. And then we subtract the V1 hat pi hat S1. And finally, we also add this term back. And we subtract whatever that is truly there. That is V1 pi hat S1. So in the previous lecture, we kind of like argued because pi hat, when we do the value iteration, essentially we finally output pi hat that is the optimal policy for this modified MDP. So this pi hat is the optimal policy for V hat. So in that case, this is like less or equal to 0. And so we are left with 2 terms, the term A and this term B. So we're mostly dealing with term A. Term B is you can actually deal with it with similar trick.
Don't you need to be greater than or equal to 0?
What?
Don't you need that thing to be greater than or equal to 0?
No, this is less or equal to 0. We will actually do, what? We'll actually do a lower, so essentially we say this is a lower upper bounded by A plus B. Because this is like a negative. So we can remove it by. You're okay? You agree with this is a negative? Yes.
I was just wondering, you already said it, so I was writing down, but in the homework we showed that had to do with the empirical variance. How does that end up being the NH instead? Is that just like the same method of showing that, or?
I think in the homework we kind of like we say for a particular SA, and this is like a upper bounded by the number of by basically n. N is the number of SA we see in that kind of scenario. So this is like just make it more general. So it allows different SA, but basically the proof is the same. It's just concentration inequality. And this is not random. This is like some given number. Okay. So essentially, to dealing with A, is just we just leverage the lemma 1 and lemma 2. So first, by lemma 1, we know A is in the A term and B term are in perfect shape of using the lemma 1. That is the difference between value V and V hat for the same policy. The A term is policy pi star, and the B term is policy pi hat. So we know lemma 1 by lemma 1, A is actually equal to expectation over pi star. Okay, so we hide the dependence of M. This is like M pi star. Okay. But let's just say directly write it as E pi star of summation H from 1 to capital H. And then we look at the pH, subject pH hat. And the important thing is now we need to look at the V hat, H plus 1, pi star, SH, H. So the next thing is we note we already decomposed the value difference to the transition difference. And hopefully we can directly use this concentration inequality so that we can directly bound the magnitude of transition difference. And the only conditions which require this either to be fixed, or the value either to be fixed or like independent of this pH. So we can look at what is this dependence. This value actually is only depends on the later transition. It doesn't depend on the prior transition because the value is kind of like the cumulative reward for the remaining steps. So it only depends on pH plus 1 hat, pH plus 2 hat, till pH hat, which in turn depends on the data of which basically data set the tuples in DH plus 1, DH plus 2, till DH. And on the other hand, this pH hat only depends on tuple in DH. So as long as we make the assumption that those tuples are collected independently, we can essentially we can essentially leverage the lemma 2 to give the bound. So we will actually later talk about, so here let's just say they're collected independently. Later we'll talk about if we have trajectory data. Essentially we can just do data splitting. Like for each trajectory, we either put it in DH or put it in DH plus 1, then we get some independent tuples. So once we have the independency, we can directly by lemma 2. We say this is upper bounded by taking expectation of M pi star summation h equal to 1 to capital H. And we plug in this bound here. And this bound is C0 times H times square root of iota and NH SA. Yeah.
So just making sure it doesn't matter that in lemma 2 you have like v and here you have v hat. Like either way, lemma 2 still applies.
Right. The lemma 2 v, like in the lemma 2, this v value function is basically arbitrary value function. It doesn't matter how it generates.
I'm not even sure that DH and DH plus 1 are independent because like when you collect the data, don't you collect it with trajectories?
Yeah, so we will actually say you can do data splitting. Data splitting in terms of like, so I actually plan to talk about it later. But basically the very simple thing is you can collect, for example, NH trajectories. H trajectories, and basically, and assign only N trajectories to each DH. So essentially, you can like divide the entire trajectories by H part, and for the first part, you only use the first tuple. For the second part, you only use the tuple at the second step. In that kind of data splitting scheme, you guarantee this independency, but you can like lose some efficiency. But this is like how you get guaranteed independence. Let's say this is data splitting to ensure independence. And use the piece. So let's continue talking about how we're going to derive the bounds. So we're already very close towards the end because we already leverage a lot of property of MDP and the concentration. So eventually what we haven't used is this like all policy concentrability. So we need to finally apply that kind of condition there. So we say this star. This star is equal to, we can rearrange the term a little bit to make it look a little bit nicer. So we move the C0H outside, and we say the summation from H equal to 1 to capital H, and we move the expectation inside. This is expectation over pi star. And finally, we'll have the square root of iota over NHSA. And by definition, we can expand out what is the expectation of a pi star. That is C0H, summation H from 1 to capital H. And then we do a summation over all possible SA at H step. Okay? And by expectation, that means a summation over all the possibilities and times the probability of that. That is a probability if we follow in a policy pi star to visit SA at H step times iota of NHSA. We just copy this. So we talk about so many things, and essentially only the last few steps are new. Last steps require a little bit of treatment because it's related to constructibility. So what we can do here is we again just we can also write this out. This NHSA is actually equal to n, that is the number of tuples we have in the H steps, times mu HSA, like the probability we visit the SA at each step. So this is equal to C0 H square root of iota over n. Like we just move some constant thing that irrelevant to SA outside. And then summation over H equal to little 1 to capital H, and the summation SA. And we have square root of P pi star HSA times P pi star HSA over mu HSA. So I just split this probability into the square root times square root. And this of the downside is mu. And we remove anything relevant to SA outside. So in terms of this form, we know it's very good in a sense. This is precisely how we assume the all policy constructibility. This is upper bounded by C. So we're taking A terms, this is like pi star. In the B term, that is pi hat. But because it's all policy constructibility, so this is again also upper bounded by C. Okay. By assumption A1, by assumption 1. So we got another thing out. Eventually, we only have this summation. So this is less or equal to C0 times H times the concentrability coefficients, C iota over n. And the summation H equal to 1, capital H, summation SA, square root of P pi star H SA. So the final non-trivial thing is we just need to upper bound this term. Okay. So upper bound this term is actually also not very hard. It's just by Cauchy-Schwarz. So we say this summation SA square root of P pi star HSA. To make it sharper, we notice this is pi star is a deterministic policy. Like in the MDP, the optimal policy is always deterministic. And in the value iteration, the B term, like when we do the pi hat is the optimal policy for the modified MDP M hat. So it's also deterministic policy. And because it's a deterministic policy, so we know this is also equal to summation over SA square root of PH pi star SA times indicator of A equal to pi star S. Okay. So only one action is actually one. Is following this policy, and the remaining actions are like assigned with probability 0. This is because this is deterministic policy. So this gives a very good form. We can use Cauchy-Schwarz inequality. Where by Cauchy-Schwarz inequality, we just have the summation AB is less or equal to AIB. Summation AIBI is less or equal to summation IAI square times summation IBI square root. So in this case, we can treat this square root of this as AI and the square root of this indicator as a BI. So what we have is this is less or equal to the overall square root of the summation SA. And when we do the square for the square root, so this we kind of make it outside. So just directly summation over PH SA and times summation SA indicator of A equal to pi star S. And we note, because this is a probability, so this is equal to 1. And this is equal to, when we summation over S, this is just a single action that make it active, so this is 1. So all we need is summation over S. So this is equal to the square root of S. So this is equal to S. So the entire thing is equal to the square root of S. So finally, we just plug in these upper bounds. So we know this, this special term is actually less or equal to square root of S. So we know this is less or equal to C0 H square root of S C iota over N. And just finally recall our choice of a number of tuples. We choose N equals to O tilde H fourth SC over epsilon square. This basically cancel out the iota term, and basically we kind of make this precisely something level epsilon. So we can make this less than epsilon over 2. Okay. And so this is a treatment for A term. And then similarly, we can do the same treatment for the B term, which we can also prove B is less or equal to epsilon over 2. And that essentially finishes the proof. So we have proved A term smaller than epsilon over 2, and with similar treatment, we can prove B term also smaller than epsilon over 2. And this essentially finished the proof. Okay, so this essentially in the offline setting is the most basic guarantees we can think of. Like we have recall that our assumption is like all policy concentrability. This is essentially like a very strong assumption. It requires your data to cover arbitrary policy. Usually it's like very difficult to achieve. And also the algorithm we run is a bit naive. Like we basically didn't modify our algorithm at all. We just ran a vanilla VI. The algorithm is a little bit naive, and we are wondering if we already know this is an offline setting, can we actually do some better algorithm? Like instead of just run this very basic algorithm, can we like leverage a structure and to do more? So the answer turns out to be yes, we actually have something smarter and something we can do better. And in order to explain the intuition, we should look at I think I will explain intuition in like a simpler setting. So can we do better? The answer is yes. So we look at we first consider the simple MDP, simple multi-arm bandit setting to gain some intuition. So in the simple MAB setting, this all policy constructibility basically says max over pi for any policy pi, for any fixed A, this is P pi A over mu HA. Okay. In the multi-arm bandit, we don't have any states and we don't have transition. So the only thing is we just put an arm. Okay. So this and we don't have like step. So it becomes the all constructibility equivalent in the multi-arm bandit. And we're saying this needs to be less than C. And because in the multi-arm bandit, if we maximize some policy for some arm A, there always exists a policy that basically just always put this arm A. So this can be make one. Basically, we can there always, for any arbitrary arm, there always exists a policy that just always put that arm. So in that kind of scenario, this is equivalent to C. For arbitrary action A, we need mu HA to be greater or equal to 1 over C. That is more or less saying we essentially need to have reasonable probability to pull any action. So this all policy constructibility essentially say we need to pull all arms relatively frequently. This is a strong assumption, but we will actually also say if we just do this vanilla algorithm, like a run vanilla value iteration, and in the multi-arm bandit case, vanilla value iteration kind of like corresponding to, I just look at the empirical average, and we just put an arm with highest empirical average. And this is essentially unavoidable. So we cannot avoid this kind of all policy constructibility for this like a naive algorithm. So we consider the multi-arm bandit. For example, we only have like 2 arms. And the first arm is the better arm. This is like the true mean. Well, the second arm is the worst arm. This is like the true mean of the second arm. However, for example, if we collect a lot of samples for the optimal arm, and this is our confidence set. But for the second arm, I don't put that like frequently. I don't put it for many times. I only put it like for 2 times. And we're getting something like here. It just happens to be very, very good. And so we have a confidence set because I only put it 2 times. So a confidence set is like something like this, like huge. And in this scenario, if we just naively do this like value iteration, or we just pull according to the empirical mean, we will actually think the second arm is better, just because empirical average, this is higher than empirical average here. So as long as one arm is really pulled, this VI, or the vanilla VI, or just like basically pick the highest, pick the arm with highest empirical mean. May choose the wrong arm. So somehow this kind of illustrates why this algorithm actually requires this kind of strong notion of coverage or constructibility. But then we can ask a question whether this is like the fault of the algorithm, whether we're doing too naive algorithm, or the problem itself is like that difficult. Like we have to pull all the arm for many times so that we can figure out what is the best arm. It turns out it's a problem of the algorithm. There is a better algorithm which requires something much weaker than all positive constructibility. So it turns out the algorithm is also something similar to what we have been talking about. In the multi-embedded setting, in the exploration scenario, we have talked about an algorithm that is called upper confidence bound, which we want to be optimism, and so that we can do exploration. So the algorithm in the offline setting is actually, interestingly, that is the opposite of that. Okay, so the better algorithm, it turns out the better algorithm is actually doing the pessimism. So it's called the lower confidence bound. Or called LCB. So this lower confidence bound means I will pick the arm with highest LCB. So what does that mean? It's essentially similar to the UCB case. We will always just consider construct a confidence set for each arm. So in this case, this is a confidence set. This is a confidence set. And for the lower confidence bound, at UCB, we look at upper confidence bound. This is upper confidence bound. But lower confidence bound is like here. This is like the lower bound. Okay? So we will actually always pick the arm with highest lower confidence bound. So it's actually not very hard to observe. In this case, it actually magically works. Like if we look at the lower confidence bound, the optimal arm actually is much higher than the wrong arm. So we actually pick the right one. So in general, you can intuitively see LCB only requires optimal arm to be put for many times. Okay. So it no longer requires you to pull all the arms like for a lot of times, like very frequently. It only requires you somehow pull optimal arm enough times. Because whenever you pull the optimal arm for enough times, you will have a very sharp confidence bound for the optimal arm. So whatever arm you pull, even if you pull a suboptimal arm, you're guaranteed the suboptimal arm is within this range. So it is like very good. Okay. So this is like the intuition. So in general, we can compare a little bit about online with offline. So we know in the online setting, we want to have the optimism because we want to do exploration. We want to explore anything that can be possibly good. So that's why we want to be optimistic. Where in the offline setting, we're given the data. We can no longer try anything new. So we just need to make a decision based on the existing data. So that's why we need to do pessimism. Pessimism is essentially saying I want to be very conservative. Essentially, that is we want to pick the action or make the decision that is guaranteed to be not bad. That is, I'm okay with like this lower confidence setup, but I'm guaranteed whatever the action I pick is going to be higher than this. So this is in a sense like I'm going to pick the arm that is not very bad. So formally, I will write down the result for reinforcement setting and formal statement and a formal assumption and skip the proof for this one. So the whole intuition is now we should not require all policy constructability. We should only require for the optimal arm or optimal policy, we can like visit it very frequently. So this is the second assumption, which is like a weaker assumption in the reinforcement learning. That is called single policy constructability. Here we say data distribution mu satisfies that max H in H, SA in SA, have the P pi star SA over mu H SA less or equal to C star. So the major difference is we no longer need to say this need to cover any policy. We no longer need to take a max over policy pi. But here we only need to cover this is like we only need it for the optimal policy. Okay. Cover a single policy, that is the optimal policy. So that's why this assumption is a lot weaker than the previous one. Like previous one, I need to hold for any policy. This is only for pi star.
So if the optimal policy is deterministic, that means you only need to cover it for the trajectory of the optimal policy.
No, the policy is deterministic, but the transition can be still random, so it's not covering like one trajectory. It still can be a distribution over state action. So now it is the algorithm. So we kind of like know in the bandit setting, we're saying we just do the lower confidence bound. So in the reinforcement learning, what we can do is so VI with lower confidence bound. Essentially a modification of VI with upper confidence bound. So more or less, we're again doing value iteration. That is, we're doing the Bellman updates. The only thing is we can like, instead of adding a bonus, we subtract a bonus. So what we're doing is this QHSA is equal to RHSA plus P hat V hat H plus 1 SA. And this is like the normal Bellman update with a transition replaced by the empirical transition. And the difference is now is we subtract a bonus here. We subtract a BHSA, where we can choose this bonus to be the same thing as we previously choose for the upper confidence bound. We say this is equal to some C0 times H square iota over NHSA. Like how many times we visited SA in our data set. And then VH hat S is equal to the max A Q hat H SA. So we can prove very similar theorem as the theorem 1 we prove, but for this new algorithm and under weaker assumption. So the theorem 2 essentially says, suppose data distribution mu satisfies the new assumption, assumption 2, and then with probability greater or equal to 1 minus delta, VI with a lower confidence bound, or pessimistic VI, outputs a policy pi hat, that is epsilon optimal, with n, little n equal to everything is the same, that h to the 4th s. Only difference is now contributivity coefficient is required to be weaker, that is a single policy contributivity efficient over epsilon square, tuples per step. So I will no longer go to the proof for the theorem, but basically you can think it's a very similar proof. Only thing is we have a weaker assumption and our sample complexity depends on something. C star is usually considered much smaller than C because C is a lot stronger requirement. Okay. So this sample complexity is actually better. and we only allow the coverage over the optimal policy. As long as we collect a lot of trajectories that's related to optimal policy, and we're in good shape. We don't really care about some suboptimal policy. You can just not visit them at all. That's fine. Okay. So finally, I want to mention a little bit about the complexity notions. Complexity we kind of talk about here. So we talk about this is the proof requires like this dh and dh prime to be independent. So typically, to achieve this independence, we already said we use data splitting. And this requires us to collect not just n tuples, but we need to collect nh trajectories. Okay, so that we can split the trajectories into like h different parts, and each parts contributes to one of the give the tuple for one steps. So this implies Vi LCB is actually requires O tilde of h to the fifth SC over SC star over epsilon square trajectories. Okay, we multiply this complexity by an additional factor of h. So it turns out the optimal policy, the optimal complexity, you can push for this setting is O tilde h cube SC star over epsilon square. So there are two h factor off. So one h factor is due to the use of bonus. We're essentially use Hopding bonus, and we already see the homework. We can fix by using Princeton type of bonus. And another actual improvement is indeed because we're doing this naive data splitting scheme to ensure this independence. This is actually a little bit of waste of the time, waste of the data. Essentially, we split the data into H pieces and only use the although we collect the entire trajectory, but we only use the transition information in one step. So there's a better way to leverage this information by using some like a so-called reference advantage decomposition. Okay. I won't go into the details about what is this techniques, but basically you should know there are techniques so that you no longer need to do this very wasteful data splitting, and you can actually shave off another h factor, and this is optimal one. Optimal one is h cube SC star over epsilon square. Okay, and this essentially finishes everything we want to talk about for the tabular setting, tabular reinforcement learning. We talk about the generative model, talk about online setting, and now finally we talk about offline setting. So in the next lecture, we will start talking about the function approximation, where if we have like infinite number of states, so in reality, like a lot of application states, number of states is like huge, or number of actions huge, and how we're gonna do reinforcement in that kind of scenario.